Okay, think about this for a second. What if the most inescapable prisons in the entire universe are actually the key to infinite energy? For decades, we've thought of black holes as these ultimate cosmic vacuums, right? Just dark maws that swallow absolutely everything and give absolutely nothing back. But what if that entire premise is completely upside down? What if, by looking really closely at the incredibly weird physics surrounding these objects, we find the loopholes that could theoretically solve our energy crises and literally redefine reality itself? Welcome to this explainer, where we're going to explore the unexplorable, the weird science of black hole environments. I am so thrilled you're here because today we're going to completely shatter some of the most common misconceptions about black holes using pure, mind-bending astrophysics. We're going to look at the solid math and the incredible observations that prove our universe is far, far stranger than our daily experience suggests. Okay, let's dive into this. Here is our cosmic roadmap for today. First, we'll look at the birth of behemoths. Second, warping space and time. Third, the quantum escape. Fourth, the cosmic whirlpool. And finally, we'll wrap up with the supermassive paradox. Let's get right into it. Section 1. The birth of behemoths, from stars to singularities. To even begin to understand how weird a black hole is, we kind of have to understand the incredibly violent stellar life cycles that forged them in the first place. A massive star is essentially this delicate, epic balancing act between two titanic forces. You've got gravity crushing inward and the energy from nuclear fusion pushing outward. For millions of years, the star happily fuses hydrogen into helium, releasing energy that holds off that crushing gravity. But as the fuel runs low, it has to fuse heavier and heavier elements in shorter and shorter time frames. And then it hits iron. Iron is the killer here. Fusing iron doesn't release energy, it actually absorbs it. So suddenly, with no outward energy pushing back, the scales tip catastrophically. In mere fractions of a second, the immense mass of the star rushes downward, striking the core like a giant hammer on an anvil, creating a massive rebound, a supernova explosion that blasts matter all across the cosmos. Now, what remains after that incredible blast depends entirely on the mass of the original star. If the mass was relatively low, you get a neutron star. This is a remnant maybe 25 kilometers across, yet it's so unbelievably dense that it packs the mass of 1,000,000 Earths into that tiny space. But if the star was massive enough, the force of the inward collapse is so profound that physics as we know it completely breaks down. The core collapses right past the neutron star phase into an infinitely small, infinitely dense point, a singularity, a true black hole. But when we see images of black holes, that big black sphere isn't the singularity itself, it's the event horizon. This is simply a demarcation line. It's the exact boundary where gravity becomes so overwhelmingly powerful that the escape velocity actually exceeds the speed of light. And because Einstein taught us that space and time are inextricably linked, this immense gravity warps space-time so severely that for an outside observer looking in, the event horizon marks the point where time literally stops. Which brings us to Section 2, warping space and time, Einstein's universe. To really grasp what's happening here, we have to shift our focus away from the mass itself and start looking at the actual fabric of space that it sits in. So the crucial point is captured beautifully in this quote by physicist John Wheeler. Gravity isn't just some magnetic-like pull. It is the acceleration caused by curving space. Imagine space as a giant taut rubber sheet. You place a heavy bowling ball on it, and the sheet curves downward, right? Any marble rolling nearby is going to naturally follow that curve. Well, the singularity of a black hole curves space-time so infinitely deep that anything crossing that event horizon is on a strictly one-way path. But here's where the physics get truly wild, leading us to a bizarre causality paradox. We naturally assume that mass creates the curve in space, like a foot creating a footprint in the sand. But Einstein's equations are proportional, they aren't strictly causational. It begs a really strange question. What if the footprint created the foot? Could the curvature of space-time actually be the fundamental reality, merely projecting what we perceive as mass? Are we all just shadows on the wall of the universe? I know it sounds completely like science fiction, but this exact paradox is highlighted by a mind-bending quantum discovery. Section 3. The quantum escape, Hawking radiation. Let's explore that quantum reality by looking at Stephen Hawking's revolutionary theory. But to understand it, I have to ask you a kind of weird question. What exactly is nothing? Seriously, if you have a completely empty vacuum in deep space, no dust, absolutely no atoms, and a photon of light travels through it as a wave, What exactly is it waving? A water wave needs water. A sound wave needs air. So what on earth is the light waving through? The answer is a quantum field. The universe isn't actually empty. It's covered in overlapping fundamental fields. Think of them almost like unstrummed guitar strings stretching across all of reality. When a string resonates, the universe expresses that resonance as a particle, an electron, a quark, a photon. The universe is essentially a ridiculously complex song being played out on these overlapping fields.
Let's move to see how this builds into an escaping black hole. Thanks to Heisenberg's uncertainty principle, these quantum strings sometimes strum themselves. Virtual particle and antiparticle pairs are constantly popping into existence out of literally nowhere, and then instantly colliding and annihilating each other back into nothingness. We've actually proven this happens in the lab with the Casimir experiment measuring vacuum pressure. But what happens if this pair pops into existence right on the razor's edge of an event horizon? Well, the black hole's violently warped space dampens one resonance, but not the other. The pairs can't cancel. Out. One escapes into space's thermal energy, and that is what we call Hawking radiation. And because energy can't just come from nowhere, the black hole pays the mass penalty. Slowly, agonizingly slowly, over trillions of years, it evaporates.
Section 4. The cosmic whirlpool. Spin, friction, and energy. The thing is, we don't have to wait trillions of years to extract energy from a black hole. Because black holes spin, they don't just warp space, they actually drag it with them. This creates a zone called the ergosphere, which is a literal whirlpool of reality moving faster than the speed of light. Physicist Roger Penrose realized you could totally use this. If you fly a rocket into the ergosphere, let the space-time whirlpool accelerate you, and then fire your propellant at just the exact right moment to escape, you could leave with 20% more kinetic energy than you entered with. It's an absolutely incredible loophole, harvesting near-limitless energy straight from the rotational power of a black hole. And this brilliantly illustrates why things don't just fall straight into black holes. When matter gets caught in that immense gravitational pull, it almost always misses the direct center and starts to spiral inward. Think of a spinning ballerina. When she tucks her arms in, she spins way faster because of the conservation of angular momentum. Space debris does the exact same thing. As it gets closer to the center, it spins faster and faster, forming a massive, incredibly flat accretion disk around the black hole. Now, because nothing can spin faster than the speed of light, this matter eventually hits a speed limit and starts violently crashing into itself. The friction here is apocalyptic. The accretion disk heats up to a staggering 10 million Kelvin. The atoms are squeezed so intensely that up to 40% of their mass is converted directly into energy. To put that into perspective for you, our own sun's nuclear fusion only converts about 0.7% of its mass into energy. This friction creates the brightest objects in the known universe. But the black hole has to shed all that chaotic angular momentum somehow, right? It does this through relativistic jets. The spinning plasma creates immense magnetic fields that act almost exactly like the rifling on a gun barrel, channeling matter and energy out of the north and south poles at near light speed. These jets can span billions of light years across the cosmos, and thanks to a lighthouse effect called relativistic beaming, when one of these jets happens to be pointed right at us, it completely outshines entire galaxies. Section 5. The Supermassive Paradox. Age and Scale. Now, what's really interesting about these numbers is the massive contradiction they set up. Look at TON 618, the most massive black hole we know of at 66 billion solar masses. Because it's almost 11 billion light years away, we're seeing it as it was in the very early universe. It literally can't be more than 2.8 billion years old in that observation. Yet, Sagittarius A star, the black hole at the center of our own Milky Way, has been sitting there growing for nearly 13.6 billion years, but it's only 4 million solar masses. So how on earth can the youngest black holes we observe be tens of thousands of times more massive than the oldest ones that have had billions of extra years to eat? The answer lies in something called Malmquist bias. Basically, we aren't seeing an accurate sample of the universe. We're only seeing what is bright enough to actually reach our telescopes. TON 618 is a quasar, an actively feeding supermassive black hole. The early universe was packed with dense gas, providing this massive cosmic buffet that fueled these blindingly bright accretion disks. Today, much of that gas is either locked up in stars or already consumed, leaving older galaxies, like ours, with quiet, dim black holes. There could be absolutely massive black holes much closer to home, but because they aren't actively feeding and glowing, they remain entirely invisible to us in the dark. Which brings us right back to the sheer unsettling wonder of this whole shebang. From Hawking radiation's slowly evaporating mass to whirlpools of space-time offering limitless energy, Black holes literally force us to question the bedrock of our physical reality. If the curvature of space can spontaneously generate particles, we have to ask again, are we simply shadows on the wall of the universe? Are we just projections of a deeper, stranger quantum geometry we're only just barely beginning to uncover? One thing is for sure. The deeper we look into the dark, the weirder and way more fascinating reality becomes. Keep questioning, keep learning, and thank you for joining me on this explainer.